All right, today's video is about writing net force equations after we have been able to draw the force body diagram and using that pictorial representation to actually start getting into solving some problems. So there are definitely some basic steps that'll help you get started. One is establishing the coordinate system that is going to be the easiest. We're going to see that, if we're doing things that are left, right, up, down, or things that are at angles, but the motion is either up, down, or left and right, we're going to choose kind of a standard XY coordinate system. But we're going to see when we start moving up and down ramps and inclines that it makes more sense to rotate our coordinate system. So establishing the coordinate system that is the easiest is really, you don't think about it, but it's important. Once we've drawn our free body diagram, it is important that we have to break forces into their components along the chosen coordinate system. So again, if you want to draw these components in, which I highly, highly recommend, you have to do that on a separate force diagram, because the force diagram is where you get the points on the AP1 exam. If you add anything else to that diagram, you will lose points. So I'm going to be asking you to do the same, and I will model that with the example problems. Okay, once we get into that situation, now we look at the sum of the forces in the x direction, and we set that equal to the mass of the object times the acceleration of the object. For these initial systems that we're going to be doing, everything is going to be equal to 0, but it's important that we start with the physics statement and then make another physics statement that these forces are balanced, so the net force is going to be equal to 0 along that x direction. And then, of course, again, when we do that in the y direction. So again, skipping the step and just saying the sum of the forces is equal to 0 is not the step you want to do here. You don't want to skip the step and make the statement of physics and then say that it's in equilibrium. All right, so we're going to go through some examples here, and I'm going to ask you, and the best thing that you can do to help yourself with this is to try this on your own, pause the video, do that, and then move on. So we have a box that's attached by a massless string here, and we're actually going to draw two force diagrams. First diagram, we're going to treat the box as our system, and then the second force diagram, I'm going to show why this is important when we have multiple string problems. We're going to treat this knot, this little joining point where all the strings, as our other system. So I'll do this force diagram. We'll do it all together, and the next one I'll have you kind of pause the video and try it on your own. So the box system, you're going to have a weight vector acting downward on the box. So labeling it force of gravity. It is also acceptable now that we know the equation for the force of gravity. I tend to always label my force of gravity as m times j. To me, it just is a lot easier to do it that way. And then, of course, we're going to have this tension force that is holding the box up. That represents this tension force right there. So these two forces are going to be equal in magnitude because it's in equilibrium. And then if we look at the knot, I'm going to draw the knot right here, just represented as a dot. And we've got T1 acting up and to the right along the direction of the string. T2 is horizontal. And then we have this tension force right here that is the same tension force over there. So that tension force is the same as that tension force, which is going to be equal to the weight of the box. So these are kind of important things. Sometimes you'll see people take some shortcuts and kind of also label this mg, but the knot itself is just m times g. As we get kind of more into this, you might be able to take this kind of a shortcut a little bit. All right, so our first step here is we're going to calculate the magnitude of T2. So this is where, we need an angle, and I think I forgot to give an angle here. So let's make this angle right here theta, and we'll say theta is going to be 30 degrees. So step 2 is breaking things into their coordinates, their components. So we have T1 is at an angle, so we break it up into its x and y components and calculate the magnitude of T2. Again, we're going to follow the steps here. So we are up to breaking the forces. If we need to redraw the diagram, go ahead and do that. And then start with these equations and then start doing your trig. So pause the video right now and give it a shot. All right, hopefully we are back. So I'm going to do a quick redraw of the knot here. So again, we've got the T1, which is going to be equal to the 50 newtons. I have my angle right here. I've got T2 off to the right. And now I'm taking my little shortcut because I know that that downward vector is actually going to be equal to the weight of the box, which ultimately is something that we're going to need to solve for. All right, drawing my components in here. I'm going to label this one T1 sub x, and I'm going to label this one T1 sub y. And again, I like to make my components dotted lines just to remind myself that these are not actual forces, these are components of forces. So once you kind of replaced this T1, it now is really completely gone anymore. I don't have to consider it mathematically because I've replaced it with the tip to tail addition of those two vectors. So magnitude of T2, we're going to do sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. T2 is going to be pointing to the right, and then I'm going to subtract the vector that is pointing to the left, which is going to be T1x, and I'm going to set that equal to 0 because my system is in equilibrium. So again, these net force equations, we're calculating the magnitude of these numbers, and we always put the direction in our net force equation. That is just standard physics practice. All right, so we know the hypotenuse of our triangle here, so now we can do a little bit of trig, and we can say that the cosine, since I'm looking for that adjacent angle, of 30 degrees is going to be equal to T1x divided by the hypotenuse, which is 50. So T1x is going to be equal to, if I plug that into my calculator, cosine of 30 degrees, that's 43.3, and we always put a unit on it as newtons, and then we plug that back in there, and now I know that T2 is the same thing, 43.3 newtons. So you never want to leave your answer as this without kind of drawing attention. So if you don't write this net force equation, you haven't really solved for T2 yet if you're skipping steps. So make sure you're not just getting the answer. All right, now we want to calculate the mass of the box. Again, that's really like a vertical component. If we look back over here at my free body diagram, flip over to a different color, this weight of the box is going to be equal to the vertical component of my tension force. So if I can solve for that vertical component of the tension force, I can solve for the weight, and then I can solve for the mass. So again, we're going to set up a net force equation. Sum of the forces in the y direction is equal to the mass of the box times the acceleration in the y direction, which is going to be equal to 0 because my system is in equilibrium. So we're going to get T1y minus mg is going to be equal to 0. And again, doing our little trig, we're going to have the sine of 30 degrees is going to be equal to T1y over 50. So T1y is equal to 25 newtons. So the weight of the box is equal to 25 newtons. And then we divide both sides by g. So that is going to be equal to 25 divided by newtons, divided by 10 newtons per kilogram. And we can see that those units work out, and the mass of the box is 2.5 kilograms is equal to m. All right, so that was the kind of hanging box problem. Next one up is the lawnmower. So we have a broken lawnmower that's actually, the wheels are busted here. So the thing is actually sliding to the right. It is sliding at a constant speed, so that tells us something about the state of motion of the object itself. Wheels are locked. The handle makes a 35 degrees. We can see that in that diagram right there. So first off, draw your force diagram of all the forces acting on the lawnmower head. You're going to write your net force equations to calculate the value of the normal force, and then finally you're going to calculate the value of the frictional force. So pause the video here and try this on your own, and then come back and we'll check our answers together. All right, we're back. Okay, so first off, the little challenging part, the lawnmower, did we get that the applied force is down and to the right because this person is pushing down on that lawnmower? Remember, the forces start at the object and move away from it. We're going to have a normal force, which is directed straight up because my surface is horizontal and it's perpendicular. My weight vector is going to be straight down towards the center of the earth. And then because it's moving at a constant speed and sliding, I really have to have some force that's going to balance out this horizontal component here. I'm not going to draw it in because that would mess up my force diagram, but there's going to be friction. And we know it's sliding, so we know it's kinetic friction, but I highly recommend you never have to put any kind of subscript or to say whether it is static or kinetic friction, so don't. Just write lowercase f, and that stands for friction. You don't never have to kind of say which type it is. All right, so moving on, and then we knew the angle here is going to be 35 degrees. So I'm going to kind of do a quick redraw of my, I'll do it over here, my normal force, my weight vector, frictional force. Here is my applied force, and then this is my angle, and I'm going to draw in my components again. I'm doing on a separate force diagram because I don't want to mess this up. This is what gets graded here. If you add these components in, you lose points, so don't do it. And then this would be FPY. All right, value of the normal force, that's focusing on the vertical forces here. So I will start with the sum of the forces in the vertical direction is equal to the mass times the acceleration, which is going to be equal to 0. We've got 3 forces in the vertical direction. The normal force is pointing up, and then I have 2 forces that are pointing down, which is going to be minus FPY and minus the weight of the lawnmower itself, and that's going to be equal to 0. All right, so let's do some calculations. Let's do some trig. I'll do it over here. This is our 35-degree angle. So that is going to be the sine of 35 degrees is going to be FPY over 120 newtons of force that is exerted. So FPY is going to be equal to 60.8 newtons. Hopefully we got that. We also know the mass of the box is mass of the lawnmower is 15 kilograms. So the weight of the lawnmower is going to be 15 kilograms times 10 newtons per kilogram, and that's going to be 150 newtons. So now we have all our numbers to solve for my normal force, which is going to be equal to 60.8 plus 150. And putting that all together, I think that, do I have a number for that somewhere in my notes? I don't. All right, I got to do that really quickly. 150 plus 68 point, oops, I messed it up. I guess I should be able to do this in my head. It's not so good. Plus 60.8. Glad I have my calculator right next to me. 210.8 newtons. Sorry for the delay on that one. All right, value of the frictional force. I'm going to switch colors because, boy, red wasn't working for me. Sum of the forces in the x direction is going to be equal to the mass times the acceleration in the x direction, and that's equal to 0. So my frictional force minus FPX is going to be equal to 0. So if I solve for FPX, that's going to tell me the value of my frictional force. And now we do a little bit of trig here again, and we get the cosine of 35 degrees is equal to FPX over 120. And FPX, which is equal to the frictional force, is equal to 98.3 newtons. So hopefully, not only were you able to get the correct answer, but you have been able to show your work. So these are the steps that I'm expecting on your WebAssign, that you start with a net force equation, which sets it equal to 0. You write out the sum of the forces, you set them equal to 0, and then you start doing the math and get the right answers. The free body diagrams also will be graded on WebAssign, so make sure you're not adding anything to it. So if you do this on your WebAssign, you will lose points. Do not add components to anything where you're asked to draw the force diagram. All right, and we will stop there.